You're watching Bowman.
I bet you weren't expecting to see Bowmaths in your exercise montage.
Hello everybody and welcome back to Bowmaths. Hope you're all doing well today. And today we're going to be doing some exercise videos on the last lecture video we had, which was using stacks to evaluate prefix notation expressions. And we looked at a few different methods for doing that, so today we're going to get used to practicing these methods and we're going to do some interesting problems. As always, I'm going to flash the problems on the screen for you to try out for yourself first, and once you do that, we can go through the problems together. Question 1. Alright, so for our first question, we're asked to compute the following prefix notation expressions using each of the three stack methods demonstrated in the lecture. And the first one we're asked to evaluate is this prefix notation expression here. So we've got some minus signs. Remember, these upside down V's are exponent symbols. And the first method we looked at was the cheating method. So let's just recall here what the cheating method is. So the reason it was cheating is because we kind of took it out of the prefix context and we put it into postfix notation. And then we evaluated the postfix notation expression using stacks. The way we do that is we push numbers or operands onto the stack. When we reached an operation, we would pop twice and evaluate because that operation would be acting on those two numbers. And we would make sure, because the stack reverses the order, that we would do the second number, then the operation, then the first number. And then when we get a number after evaluating that, we put it back onto the stack and we repeat this process. We've done this several times over a couple different videos, so it's a process that we're a bit more familiar with, and that was kind of the appeal of this cheating method. So let's go ahead and do it for this part A here. Alright, so I've got it written out here. Let's do it step by step. So the first part is to convert from prefix into postfix. So here we have our prefix notation expression written out, and we want to convert it into postfix. So the way we're going to do that is we're going to start by looking at, okay, what operations happen first here. So we note that we have an exponentiation of 2 to the power of 2. That's kind of the first group we can look at. Right, this minus sign isn't going to happen until after we've evaluated these. Right, if we do exponent 2, right, 2 to the power of 2 here, we're just going to rewrite that into postfix notation, and we do that by doing, okay, 2, 2, and then the operation comes afterwards, right, instead of before. Similarly here, we have exponent 7, 2, so this is 7 to the power of 2. So when we rewrite this down here, we keep the 7 and the 2 in that order because we're doing 7 to the power of 2. If we change the order, 2 to the power of 7 is something completely different, right? So we want to keep the order of the numbers, but the operation is coming after those numbers, right? And then the third thing that we're going to be doing is we're subtracting. So the subtraction, being an operation, now comes after, and we need to make sure we're keeping the order, right? Here we would be doing the result of this first group here minus the result of this second group. So we need to make sure that we still have the first group and then the second group in front of this minus sign here when we've converted from prefix into postfix. So hopefully that's just a bit of a review on prefix to postfix. We have some dedicated videos and content on that topic already. So now we're going to get into, well, what's the next step? We have it in postfix notation. We can do step 2 here, which is to evaluate using stacks, but evaluating our postfix notation expression. So we just push numbers on until we reach an operation. So we push the 2 on, right? This green arrow here is representing it's the top of our stack. Then we push our second 2 on. Okay, nothing exciting so far. Now we've reached an operation, right? So with this operation here, we input that, and that tells us to pop twice to access the numbers, right, this 2 and this 2, that this operation is going to be acting on. So when we do that, it leaves our stack empty, right, because we've accessed both of the pieces of data in it. So we get this 2 and this 2, and then we evaluate 2 to the power of 2 because the operation was the exponent operation. And here it doesn't really matter because the 2's, it's the same thing, but order does matter with exponents usually, right? It's just we have the same number here. So do note that it's the second number first, right? That's this green 2 here. And then we do the first number afterwards, right? So the first number that we popped, this top 2 here, that comes second. So 2 to the power of 2 is 4, so we push that result onto the stack. So now this is what our stack looks like after doing step 3. All right, so now we keep scanning. We've done these three. We have a 7 now. So we push 7 onto the stack. And we have a 2, so we push 2 onto the stack, right? So every time we push onto the stack, it goes on top of the stack, right? So that's why our stack is sort of being built up like this. And next we have another operation, another exponent. So we input the power operation, which tells us to pop twice. So we get the 2 first, right? Because that's at the top of the stack. Then we get the 7. So 2 first, then the 7. And so to do the operation now, we make sure we do the 7 first to the power of the 2 second, right? We have to keep that order of the second number operation, then the first number. So we do 7 to the power of 2, keeping with the order that we saw the 7 and the 2 come in the expression that we're inputting. 7 to the power of 2 is 49, and that result gets put back onto the stack. So now we have just one operation left, this minus. So we input the minus, which tells us to pop twice. So we get the 49 first, and then we get the 4. And our stack now is empty, which is good because we have nothing else to put in. So we have the 49 and the 4, and we do the subtraction, right? So the second number comes first, we get a 4. First number comes second, we get the 49. 4 minus 49 is negative 45. So this process tells us that the answer is going to be negative 45. Okay, so now if we do this with other methods, we should still be getting negative 45. It's just that the steps along the way are going to look a little bit different. So for the second method, we're going to be using the stack purism method. And recall with this method, it was nice because we could immediately use stacks and we didn't have to do any converting. But the caveat is we'd have to push both operands, right, numbers, and operations as well onto the stack. So not just numbers, but also the actual symbols themselves that are combining the numbers. And then when there were 2 adjacent numbers, we would pop 3 times to get the numbers and the operation acting on that stack. And then we would do the evaluation in this order here and push the result back onto the stack. So let's see what this looks like in our same example, and hopefully we get negative 45 as well. All we're going to be doing is going through this expression here, and every time we see an operation or a number, we're going to push it onto the stack. So we start with the minus here, and we push the minus onto the stack. Next up, we have the exponent operation. All right, we're just going to push that onto the stack as well. Nothing interesting yet. We're going to take the 2 now and push that onto the stack. Okay, we've done that. Still nothing we can do, right? The only time we can do something is when we have 2 adjacent numbers, which we're about to get when we push this 4th 2 onto the stack. Now we have 2 numbers side by side here. So what we have to do is we have to pop 3 times. So that gives us these 2 numbers, the 2 and the 2, but it also gives us an operation to work with, right? That's going to give us this exponentiation operation. So we have a 2, and we have an exponent. And what that leaves our stack with, now that we've popped these top 3 elements, is just this minus right here. Okay, so we evaluate 2 to the power of 2, right? Keeping in mind we're actually doing the second 2 popped first, right? Second number, then the operation, and then the first number we popped, so that's this blue 2. 2 to the power of 2 gives us 4, and that 4 we're going to push onto the stack here. So we have a 4, and we have a minus now in our stack. Okay, so let's keep going. Next up, we have an operation to input, so we push the exponentiation operation, and then we push the 7 onto the stack. Now, we do have 2 numbers, but they need to be adjacent numbers, right? So as such, we just keep going. We keep pushing. And we only have one more thing to push. We have a 2, so we better hope we can do some stuff now. And so we push the 2 on, and sure enough, we can do some things because we have a 2 and a 7, 2 numbers adjacent to each other. So we're going to pop 3 times. That's going to give us the 2, the 7, and the exponentiation symbol, leaving our stack with just the minus sign and the 4. So now we do 7 to the power of 2, right? Second number that we popped first. 7 to the power of 2 is 49, which we push back onto the stack. But what this does is it gives us 2 adjacent numbers yet again. So that means we have to pop 3 more times, making the stack completely empty, and we get the 49, the 4, and the minus sign. Again, evaluating in the proper order, we get the 4 minus 49, which gives us negative 45, just as we got in the first method. Okay, so now we have one more method to do for this part, and that is the postfix wannabe method. Okay, so postfix wannabe was not quite where we would convert from prefix into postfix, but we did sort of change the way the expression looks, and that is by reversing the order first. And then we do something very similar to when we were evaluating with postfix notation expressions, right, where we push numbers onto the stack, and then when we get an operation, we're going to pop twice and evaluate. but we do a different order for evaluation. In the cheating method, we do the second number first and then the first number that we popped afterwards. But in the postfix wannabe method, we don't do that. And we explained why that happened in the video, where here the stack reverses the order of the numbers. So we need to unreverse it by changing our order when we evaluate. Whereas here, the stack does do that, but we reverse it in the first place, right? So we flip twice, that takes us back to where we started, right? That's why we can actually keep sort of a more natural order when we're evaluating with this postfix wannabe method. So let's go ahead and evaluate this expression now using this third method here. So we start by reversing the expression. So, 2 is last, so it comes first here, then the 7, and so on and so forth. So this expression is completely backwards now. And now we just go ahead and we start pushing things. That's what we do with stacks. We push. So we push the 2 on. Great. We push the 7 on. Nothing interesting. But now when we input an operation, that leads us to popping twice to access our numbers and to actually evaluate something. So our stack is now empty because we only had 2 numbers in there and we just popped both of them off the stack. So we get the 7, then we get the 2. And now, keeping with the same order that we popped them in, right, we do the first number popped, then the second number popped. We do 7 to the power of 2, which gives us 49. And we can push 49 right onto the stack there, and we can proceed to our next input, which is a 2. So, being a number, we push that onto the stack, and we get 2 and 49. Then we get another 2, also a number, so we're going to push that onto the stack. And next up, we have the exponentiation symbol. So that's an operation. So when we input that, we're going to pop twice, which is going to give us the top 2 pieces of data, this 2 and that 2. And we're going to evaluate them. 2 to the power of 2 is 4, which we then push back onto the stack. Next up, and lastly, our last input is a minus operation. So we pop twice again, making our stack empty. We get a 4 and a 49. So then we subtract them in the order that they come, and we get negative 45, same as we got with the other 2 methods. Okay, so that's everything for this example. All right, so once again, we start with the cheating method. We see here we've got a bit of different numbers, different operations this time. So let's see what this looks like. With the cheating method, we start by converting from prefix to postfix. So here's our prefix notation expression here. And we're going to start with this plus 5, 7. So the plus 5, 7 just becomes 5, 7 plus, right? The order of the numbers stays the same, but the operation comes after instead of in front. Similarly, this minus 5, 2 becomes 5, 2 minus. And then lastly, we're doing this entire first group here divided by this entire second group here. So we keep the first group and the second group in that order, but the division sign now comes after as our third operation that we do. Okay, so now that we have converted from prefix to postfix, we can start doing stack stuff. So we're going to start by pushing numbers onto the stack. So we have a 5 here, we push the 5. We've got a 7, we push the 7. You know the drill by now. We've got a plus sign, that's an operation. So we're going to pop twice, which is going to give us this 7 and this 5, right? Our 7 and the 5 that were on the stack. But because stacks reverse the order when we're popping, 7 and 5, whereas when we started we had a 5 and a 7, we need to also reverse that order, as we've been saying all along. So 5 plus 7, right, our operation was the plus, and that gives us 12. So we push 12 onto our stack. Okay, so we've done these 3. Next up is our 5. So we push 5 onto the stack. That's our new top, indicated by the green arrow. And then we push the 2 onto the stack, which gives us a 2. Once again, our new top now. So now we've got an operation of minus. So we pop twice, getting our 2, that's the top, and then getting a 5, because the top then goes to the 5, which once again gets popped off right there. Reversing the order, we do 5 minus 2, and we get 3, which we then push onto the stack. And then for our last step here, right, we've got our division left over. Once again, it's an operation, so we pop twice, giving us a 3 and a 12. Reversing the order, we do 12 divided by 3, which is 4. So our answer for this expression here should be 4. So hopefully, with the other 2 methods, we also get 4 as our conclusion. All right, so we're doing stack purism now. So only stacks, no funny business beforehand. Okay, so we're going to be pushing everything onto the stack, including operations, right? I really like this method. I think it's cool that we're sort of treating these operations as their own individual things, because normally when we're doing math, operations always have to be accompanied with numbers, right? But here, we're kind of treating them by themselves, and I think it just looks cool. But maybe that's just me. I am a bit of a giga nerd. Okay, so we've got a division sign. That's our first input, so we push the division sign onto the stack. Next up, we have the plus sign. Also an operation, just push that onto the stack. Remember, with this method, nothing happens until we have two adjacent numbers. So we're going to push this 5 as well, and push this 7 for steps 3 and 4. But once we push the 7, that gives us two adjacent numbers. So we pop 3 times, which gives us the 7, the 5, and the plus, leaving the division sign all by itself. And then when we evaluate what we've popped, we do the 5 plus 7, which gives us 12, which we push back onto the stack. Alright, so we've done these first 4 inputs. Next we have the minus sign. So we push the minus sign onto the stack, and then we push the 5 onto the stack. Okay, we still don't have two adjacent numbers, so let's keep going and push the 2 onto the stack. So here, we have two adjacent numbers, our 2 and our 5. So we're going to pop 3 times, which is going to give us 2, 5, and then the minus sign, just these top 3 pieces of data from the stack, leaving the division sign and the 12 in the stack by themselves. And then reversing the order, we do 5 minus 2, which gives us 3, and that gets pushed onto the stack. But what this does is it gives us two numbers yet again that are adjacent. So we pop 3 more times to empty the stack completely, and then reversing the order, we do the 12, right? Our second number popped, divided by 3, our first number popped, to give us the same answer we got before, 4. Okay, so now we have the postfix wannabe method. So we're going to start by reversing the order of this expression, right? So division sign is first here, that's what comes last. And so on until we get to the last 2 becoming our first 2. Okay, so now that we've reversed the order, we can start pushing numbers onto the stack. Unlike the last method, it's only numbers we're pushing, right? No operations. Operations are going to lead to popping, just like they do in the cheating method. So step 1, we push our 2, great. Then we push our 5 in step 2. And then when we get to step 3, we're inputting an operation, which leads us to popping twice, emptying out our stack, and getting 5 and a 2 in that order. Then, in this method, right, we keep the same order, so we just do 5 minus 2, which gives us 3, which we push back onto the stack. Next up, we have a 7. 7 gets pushed onto the stack, and we also have a 5, which gets pushed onto the stack. Numbers don't really do much, they just get pushed on. It's only when we get to an operation, like in step 6 here, when we actually do some popping, right? So we input the plus, and we pop twice to get our 5 and our 7. In that order, we add them. 5 plus 7 is 12, which we then push onto the stack. And then we get to our last step here, which is division. So we're going to input our division sign. Division being an operation tells us to pop twice, which gives us the 12, then the 3. And then dividing in that order gives us 4, exactly what we got in the last 2 methods. So that's all for part B. Now we got to do part C, which I think is a little bit cooler. Now you might be thinking this is a little bit repetitive, and it kind of is, but it's important to just do this over and over and over again to really cement this stuff in your mind. Because, well, you know, the more you do it, the more you remember it. Even me doing this, I mean, I've done these kinds of problems like hundreds of times, but by doing them every now and again, it allows me to remember them for a longer period of time. Let's say I don't do math for another 20 years. Maybe 20 years down the road, I'll still remember how to do this because, well, I practiced it enough. So let's get to cheating. So this one has a little bit more work, so I had to split it up into a couple pages, but the first part here is we start by converting from prefix to postfix. We've got 4 minus operations here, and we are just going to evaluate them from right to left as you do with prefix notation. So the first thing we do is 13 minus 2, so we write that in postfix notation like this. And then we're going to be subtracting the 5 from that. So we write the 5 next, and then the subtraction that's going to be acting on this first group's result and the 5. Next up, we're subtracting this 1. So we write the 1 and then the subtraction operation after. And then lastly, we're subtracting this 6. So we write the 6 down and then the subtraction operation. So this is our new expression now that we're going to be evaluating using a stack. So maybe I'll just move this up a little bit and make some room for step 2. So this is the expression that we're looking at. So we start by pushing the 13, then the 2, and then we have an operation that we're inputting. So we pop twice to get that 13 and the 2. in this order, 2 then 13. Then, reversing the order, we subtract them to get 11, and we push that result onto the stack. So we now have 11 in our stack, and when we push the 5, we make 5 our new top. And then we input the minus sign next, which is going to tell us to pop twice to get that 5 and that 11. Once again, our stack is empty here. So we get the 5 and the 11, we subtract them in the order of 11 minus 5 to get 6, push that onto the stack. Next up, we input the 1, so that gets pushed onto the stack. I wrote input here, but I want to be consistent and write push, so I've got push right there. And then we subtract in our 7th step here, so we pop twice to get the numbers we're subtracting, the 6 and the 1, subtract in this order to get 5, and we push 5 back onto the stack. Okay, we have one more number to combine with this 5 here, and we're going to do it with subtraction. So we push the 6 onto the stack, getting our operands or our numbers ready to go, and then we input the minus sign, which is telling us to subtract, so we pop twice to get our numbers out, leaving our stack empty. 6 and the 5, evaluating in the opposite order with the subtraction, we do 5 minus 6 to get negative 1. Okay, so negative 1 then should be our final answer for any of the methods to part C here. Let's find out if that's the case. You'd be pretty disappointed in me if it wasn't the case, I guess. Okay, so let's go ahead and use stack purism here. So here, just pure stacks, we're going to be pushing operations and numbers onto the stack. So we start with this first minus sign, push it onto the stack. Second minus sign, push it onto the stack. Third minus sign, push it onto the stack. Fourth minus sign, push it onto the stack. Alright, so that's a lot of pushing so far, and we still got 2 more because we can't do anything until we have adjacent numbers, right? So we've got a 13, push it onto the stack. Got a 2, push it onto the stack. But now we have our adjacent numbers, right? So this looks kind of goofy, or I think it looks pretty cool. You might think it looks dumb, I don't know, but like just all these minus signs like sort of slowly building up, ready for battle. I think that's sort of a cool aesthetic. And don't you forget it, aesthetics is a big part of math. Okay, so we've got our stack here. We've got 2 adjacent numbers, our 2 and our 13. It's time to do some evaluation. So we're going to pop 3 times to get the 2 and the 13 and a minus sign. So we're going to have just 3 minus signs left over. And we're going to make sure to evaluate in the opposite order. So we do 13 minus 2, which gives us 11. And we push 11 back onto the stack there. So now we have 1 number, so we have to keep pushing. So, well, we did the 13, we did the 2, now we have the 5 to push. So we push 5, and that gives us 2 adjacent numbers. So we can pop 3 times, giving us 5, 11, and another one of our stored up minus signs. So we do 11 minus 5, right, switching the order. 11 minus 5 is 6, and we're going to push the 6 onto the stack. All right, awesome. Once again, we need another number to do anything, so let's just keep pushing, because next up is another number. So we push the 1, we get 1 and a 6, 2 numbers there, so we pop 3 times to get those numbers and another minus sign, which leaves us with just 1 last minus sign, so there's only 1 more step after this. So we do 6 minus 1, which gives us 5, and we push the 5 onto the stack. There's still 1 more step, so step 9 is we have our last 6 here, so we push it onto the stack, which, again, 2 adjacent numbers, pop thrice, 3 times. We get a 6, we get a 5, we get a minus sign, completely emptying out our stack. And then evaluating 5 minus 6, we get negative 1, same as in method 1. Let's move on to the third method. Alright, so our first step with postfix wannabe is to reverse the order. So we do reversing the order, right? All of our operations come afterwards now, and the numbers are in the opposite order. Okay, so now we just start by following this new order here and pushing. And even though the operations come after, this isn't a postfix notation expression, right? Because the numbers are in the wrong order. That's why it's postfix wannabe. So always remember that. This isn't actually postfix. If you want to go through postfix, you have to use method 1. But anyways, we're going to go through now. So we push the 6 onto the stack, then the 1, then the 5, then the 2, then the 13. Okay, so a lot of pushing again. But when you're pushing numbers, nothing happens with this method, right? It's only when you input a operation. So we're just loading up our stack here. And now we've got 4 operations in a row, so we're going to be reducing this thing now. So we input a minus, which tells us to pop twice, we get a 13 and a 2. And remember, because we flipped our order once, and then going through the stack and popping flips it again, we can keep the order that we get after popping, right? So we get the 13, then the 2, so we're going to do 13 minus the 2. And we get 11, which we push back onto the stack. We input our second minus sign, which tells us to pop twice, giving us the 11 and the 5. And then evaluating in that order with subtraction, we get a 6, which we push back onto the stack. We've got our third minus now, so we input that, which we pop twice to get a 6 and the 1. Doing 6 minus 1 gives us 5, which we push onto the stack. So now we have 2 numbers left, 1 operation left. This is going to work out perfectly when we slide step 9 on into there, where we input a minus sign, popping twice to get our 5 and our 6. 5 minus 6 gives us -1. So method 3 gives us the same result. And if you want some extra practice, make your own prefix notation expressions, right? Make whatever you want, as long as they're in prefix notation, and then try and evaluate them with these methods. So you have infinite practice at your disposal. Feel free to share some of the problems you come up with and your answers in the comments, and then you can practice with other people as well.
Question 2.
Okay, question 2. I hope this isn't too small to read, but I'll read it out loud. It looks really long, but it's actually not too bad. So you want to make a new method for solving postfix notation expressions using stacks, and you were inspired by the cheating method for solving prefix notation expressions. In your method, you decide to convert the postfix notation to a prefix notation expressions, and then use stacks to evaluate the expression. Recall, the cheating method in prefix notation is we convert from prefix to postfix and then use stacks. So what we want to do here is make a method where when we start with a postfix notation expression, we go from postfix to prefix and then evaluate using stacks. So which of the 3 methods could be used to enter an infinite loop where you don't get a solution? So what this question is really asking us is, once we convert from postfix to prefix notation, we're going to need to use a way to evaluate the prefix notation expression using stacks. And we have 3 methods for that, right? So the question is out of these 3 methods, once we've converted into prefix, which one, if we used it, could be used to enter an infinite loop where we aren't getting a solution? So postfix into prefix, then we use one of our methods, but one of these could cause a problem. Let's first of all quickly talk about what an infinite loop is. So you may have heard the chicken and the egg argument. The idea is that an egg, in order to get an egg, you need a chicken to lay the egg, right? But in order to get a chicken, well, you need it to have hatched from an egg. Okay, so we need an egg. But in order to get an egg, you needed the chicken to lay the egg. And so the question is like, what comes first here, right? It's just sort of this infinite cycle. And you can, if you want to talk about like origins of life and everything, there can be an answer, but the point is that there's sort of this loop where to answer one question, you need to answer another question, but that relies on the previous question, right? So you kind of get trapped in this cycle here. And so we want to see, can we also get trapped in a sort of cycle, an infinite loop, when we're trying to come up with this method here? Okay, so the idea is we go from postfix to prefix with our new method, and then we use one of the other methods that we've learned and been practicing today to evaluate in postfix notation. So if we take a postfix notation expression and we put it into prefix notation expression, how could we enter a loop with this? Well, if we went back from prefix to postfix, and then we went from postfix to prefix and back and forth, right, we could enter an infinite loop that way. So what method gets us to go from prefix to postfix? Well, that's the cheating method, right? Recall, the cheating method tells us our first step is converting from prefix to postfix. So now imagine this. Our first step is going from postfix to prefix in our new method here. But then when we use the cheating method, it tells us, okay, well, our next step is to go from prefix to postfix. So we're back at postfix. Well, our method tells us when we're in postfix, we need to go into prefix. So let's go to prefix. Oh, but now to solve the prefix notation expression, cheating is telling us to go to postfix, right? So do you see how we're sort of getting caught in this infinite loop here, where by combining this method of converting from postfix to prefix and then using this method here where we're going from prefix to postfix, we sort of get stuck where to do one, we need the other. but to do the other, we need the first one and we don't get anywhere, right? So this is one thing to always consider whenever you're coming up with methods or you're trying to do math, is you can sort of end up getting stuck in this cycle where to do one thing, you have to do the first thing and go back and forth. And so this would be an example of coming up with a method that actually wouldn't work. If you gave a computer to do this, it would just keep running and it wouldn't give you anything. You would get some sort of error. And so if you wanted this to actually work, where you start with a postfix, you convert to a prefix method, and then you evaluate with a stack, then you would want to use either method 2 or method 3, because those, once you're in prefix notation, they stay in prefix notation, right? They don't convert back into postfix. They do their own computations. So those would be safe to sort of chain into this first step of doing postfix to prefix. But if we wanted to chain the cheating method in there, then you would enter an infinite loop. Question 3. All right, so let's get into our third and final question for today. Only 3 questions because the first one took a while. So this one says, give an example of a prefix notation expression in which the cheating method and postfix wannabe methods have all the same steps. Okay, so this one's interesting because cheating and postfix wannabe are 2 different methods, but we know that when we've done all the methods, it's been similar, right? We maybe sort of rearrange the expression in some way, and then we do pushing and popping, right? So the question is, can we come up with an example of a prefix notation expression where we actually get the exact same steps in these 2 methods? So let's do a quick side-by-side comparison of these 2 methods to see what we need. First of all, the first step, we convert from prefix to postfix in the cheating method, and in the postfix wannabe method, we reverse the order. So the first thing we need to have is to make sure that this first step of converting from prefix to postfix and reversing the expression order are the same. In a lot of cases, it's not the same, but there might be specific examples where these are the same thing. So try and think about what that would look like. And then the second part is quite similar, right? We push numbers onto the stack. When we get to an operation, we're going to pop twice and evaluate. But once again here, we have to be careful. The main difference is that in the cheating method, we do the second number we pop, the operation, then the first number we pop. Whereas in the postfix wannabe method, we do the first number we pop, the operation, and then the second number that we pop. So we have to somehow make sure that this is also the same in both methods. Okay, so I've written down our similarities and our differences here, summarizing what we just said. And so how can we resolve these issues? Well, let's actually start by looking at this second difference here. I think this is going to be the easiest one to fix. So how can the second number, operation the first number, be the same as the first number, operation the second number? The operations are the same, so that's not a problem. It's just these numbers that are different. Well, what if the numbers aren't different? We saw that in some earlier examples that when we had something like 2 minus 2, it didn't matter which one it came first, right? The first 2 or the second 2, it's the same number, right? So we can resolve this issue if our second number equals our first number, right? Then these are the exact same steps, right? If my second number is a 3 and a first number is my 3, well then in the cheating evaluation, I do 3 operation 3. In the postfix wannabe evaluation, I do 3 operation 3. It's the exact same thing, right? Okay, so that resolves our second issue. And we're going to find that actually will also help us with our second issue, because we saw that when we reverse the order of an expression, the operations moved into kind of a postfix setting, but the numbers, the order being reversed was a problem, right? But now, if it doesn't matter the order of these numbers, because we're making them the same as each other, then it won't really matter when we reverse their order either, right? And all that's going to change is the location of the operation, which is exactly what we want for postfix. So just to keep it simple, because all we need to do is an example, let's just use a single operation, so like something like 1 plus 1 or something like that, in our example, and making sure to use the same number so that both of these get satisfied, and we'll see that both methods have the same process. Let's do divide 7, 7. So this is our prefix notation expression. We only have one operation, and we have the same number. Okay, so let's see what this looks like with the cheating method. So the cheating method tells us to convert from prefix to postfix. So we put our 7s over here, and we put our operation after the expression instead of in front. And then we're supposed to push the numbers onto the stack. So we push the first 7 and then the second 7. And then when we input a division, we pop twice. We get a 7 and a 7. And then via the cheating method, we're going to do the second 7 first, divided by the first 7, and we get 1. Now let's compare it to the postfix wannabe method. So once again, we reverse the order, and we see here, because we used only one operation, and because we have the exact same numbers here, right, the 7 is the same as that 7, we get that reversing the order, right, like putting this 7 here, this 7 here, this division here, gives us the exact same expression as if we converted this into a postfix operation expression. Next up, we want to push the 7, right? We just push numbers onto the stack in this method as well. So we push the 7, we push the 7, and then we input our division, which tells us to pop twice. So all of these are the exact same. The only difference could come in with these orders being different here. So when we evaluate, we do the first 7 divided by the second 7. But because these are the same number, we see it doesn't matter, right? Even though this is technically the first 7 and this is technically the second 7, we get the same expression overall, right? And that's what this question is asking for. And we get 1 in both cases, right? So we see this is an example of an expression in which the cheating method and postfix wannabe method have the exact same steps when you just look at it on the surface, even though they're technically doing different things, right? This is reversing the order. This is converting to postfix. This is technically doing the second number and then the first one. And this is technically doing the first number, then the second one. But because of the way we've structured it, it looks the exact same. So see if you can come up with some other examples, maybe ones that are a little bigger than this, that also get these methods to have the same result as each other. I'd be interested to see what you come up with in the comments.
Concluding thoughts.
Okay, that's going to do it for me today. Thanks for watching, everyone. Hopefully you feel more comfortable with these topics. Let me know any thoughts and feedback that you have. I'm looking forward to continuing to make some more videos for you. And I also changed up the presentation style a little bit today where I had everything pre-written out, just hopefully to make it a little bit smoother and to not make so much noise when I'm writing on the table because my microphone picks that up. So without further ado, thanks for watching. Have a good one. You stay groovy, and I'll see you in that next BOMAS video.
BOMAS.